Welcome to ISY 6382. We continue control phase and control chart with learning more about different types of control charts and specifically variable control charts in this lecture. So let me start with two types of control chart or two types of quality characteristics that we have. One is variables, which is continuous measurement. So as you know, when you do the measurement, the output of measurement would be basically a continuous continuous number. It has a unit most of the time. For example, could be for mass could be pound, for length could be inch, and for time would be second. And for those quality characteristics, we use x bar r, x bar s, x bar s squared, and xmr control chart. And in this course, we learn some of these control chart, how to use them. For attribute data, the output of the inspection is defined or represented by discrete data. So either it's conforming, non-conforming, okay, not okay, which you learned in measure phase or statistics review, that usually we use Bernoulli and binomial distribution for modeling them. Or it's count of number of non-conformities. For example, you count the number of scratches on the surface of painted body in a paint shop. And for that, we use P, NP, and C control chart, and we learn how to use them for monitoring the process based on discrete data or attribute quality characteristics. Quick review, if you remember, we had the term chance causes, which means if the process is performing only under chance causes, the process is in control, and which means that both mean and variance are constant over time. That's sort of like a statistical definition. So both mean and variance constant over time, it implies the process is in control, which means we have only chance causes. If something happens in the process, if we have some assignable causes, it basically changes either mean or variance or both of them, which implies that the process is out of control. So based on the definition of process being out of control, we have two terms. One is mean or variance. So that's why we need to have two control charts, one for monitoring mean and one for monitoring variance. And as you can see, we have different pairs of control charts. The left side are control chart used for monitoring mean, okay, and the right side are the set of control charts used for monitoring variance or variability of the process. So short control charts, the main assumption is they are coming from a normal distribution. So the measurement that you have is coming from a normal distribution. If they are not coming from a normal distribution, we can do some transformation as you learned before in the measurement phase, for example, Box-Cox transformation or Johnson transformation. And if they're coming from a normal distribution, then mu plus k sigma is UCL, and mu minus k sigma is LCL, because it's symmetric, and the center line is mu. And usually we use k equal to 3. Why? The reason is if we use k equal to 3, when the process is in control, almost all data or measurement are expected to be between this interval, 99.73% of basically measurement or data points, to be exact. Sometimes we use k equal to 2 as warning limits, which means if the data point is beyond the warning limits, the process is not out of control, but we should be basically a little bit more careful, because in the next few samples we may see some out of control points. All the equations that we have here to find control limits depends on mu and sigma. So the main assumption is we know mu and sigma, but in practice we don't really know these values. So what should we do? We need to collect some data, and we need to use this data to estimate mean and variance of the process. So this is called phase 1 of control chart. So in phase 1, we collect data, and it's kind of like historical data, and then we try to estimate basically mean and variance and find the control limits. However, the data set that we collect could include contaminated data, meaning that some of the data are coming from out of control process. So there are some assignable cause associated with that. One thing else that we do in phase 1, in addition to estimating mu and sigma, we want to identify those contaminated data or those out of control data and removing from our data set in order to get a better estimation for mean and variance and more accurate value for control limits, LCL, CL, and UCL. So as I said, we have some objectives in the phase 1. of control chart. One is to estimate the distribution parameters of the monitoring statistics, namely mean and variance, to determine the baseline control limits, which means make sure that we estimate mu and sigma correctly, and based on that we get mu, UCL and LCL. And we call it baseline because it's a baseline for phase 2 monitoring. And the third objective is to stabilize the process through removing assignable causes. So as I said, there could be some data coming from out of control situation in phase 1. We identify them and we find the assignable causes associated with those data, and then we remove them. By that, we can stabilize the process before starting real-time monitoring, which is phase 2. So at the end of phase 1, we have baseline control limits. We can use that to do monitoring. So phase 2 is sort of like a real-time monitoring. By that I mean, every time we go and collect data and basically use this data and plot a point on the control chart whose control limit obtained from phase 1. Okay, so it's like one point at a time, one sample at a time. And it's in sort of like an online or real time. And every time that we collect a sample, plot it, we can evaluate whether the process is in control or out of control. Because in phase 1, we are collecting data for, let's say, a week worth of data. And then when we do analysis, we understand that, for example, 3 days ago, the process was out of control. It's more offline setting. It's not useful for online. It's just being used for finding the limits for phase 2, which is online. Okay, with that introduction, now let me continue with phase 1 control chart and how we can use phase 1 for estimating the control limits and finding or achieving the goals that we have for phase 1. So first of all, we need to find the control chart that we are interested in. So based on the quality characteristics, whether it's attribute or basically variable. The next step is to find sample size, number of samples, and sampling interval. Okay, here is one example. So let's say we have one basically check sheet. We have sampling time 8 in the morning. We start the sample. So what we want to do, we want to collect 25 samples. Okay, so your M in this case is 25. And each sample includes 5 parts. So we select 5 parts, we measure them, and I have 5 numbers here. The sampling interval in this example, so our N is 5. Let me finish this. And the sampling time, the sampling interval, which is time between samples, is 15 minutes in this case. So based on this strategy, we go ahead and collect data. So we collect 25 every 15 minutes, and each sample includes 5 observations. That's the data collection plan that we have. These are the data that we are going to use to estimate the parameters. So what we do, after collecting the sample, we estimate the parameters mu and sigma. I'll tell you how. So for each different control chart could be different. And for example, if you are using XBAR and R control chart, so we calculate for each sample the average, which is XBAR, and the range, which is R. And after that, we can calculate X double bar, which is the average of averages, and R bar, which is the average of ranges. After finding mu and sigma, we can find the trial control limits. Why do we call it trial? Because we are not sure if the data that we used for finding these control limits are in control. That's why we call it trial. And using this trial control limit, we plot the control chart. Let's say we plot XBAR and R control chart. 2 control charts, one for process mean and the other for process variance. So what we see, for example, some points are out of control, and let's say R is everything is in control, or maybe some points here are out of control in R. So what do we do in these cases? We find out of control points. What are the root causes of those assignable cause or those out of control points? Then we take corrective action to make the process back to normal and make sure that root causes do not exist. For example, if root cause is based on the training of the operator, we make sure that the operator is trained. Or it's because of the sudden change in temperature, we make sure that that wouldn't happen again by setting up some temperature controller or something like that. If the process is in control, or if all the points are inside and there is no random pattern, we consider the trial control limit as a basically baseline control limit or finalized control limit. However, if some of those points are out of control, as I mentioned, We need to find the root cause and take corrective action. And finally, we remove those points. This is very important. So if I have these points out of control, these points out of control, and then I need to remove those points and redo the calculation. By that I mean we need to recalculate control limits again and plot the remaining points, and we repeat this procedure until no new points are out of control. If this loop is repeated several times, as you can see, and then we finally go, everything is in control, that would be our baseline. So this is called phase 1 monitoring. Based on that, we can use the baseline control limit, which is used for phase 2. Let me start with first control chart, which is X bar and R. So this is X bar control chart, and this is phase 1. And what we need to do, we need to estimate basically mean and variance based on the data that we have. So we have, if I go back to the data sheet that we had, you remember we had sample 1, sample 2, sample 25. Usually M is 25 to 30. If you can get more data to 50, it's also fine. And we have X1 to Xn, which is the sample size for each sample. And what we do, we calculate X bar, and we calculate R of each sample, and finally we calculate X double bar and R bar. So X double bar is a good estimator for mu. So the mean of the process is summation of X bar divided by the number that we have. So that's how we estimate mean. For standard deviation, however, what we do, we use R bar value, but R bar is not a good estimator for sigma. Statistically speaking, is biased estimator. To make it a good estimator or unbiased estimator, what we do, we divide it by a constant, D2, and this constant is a function of your sample size. And there is a table that you can see. Based on that table, you can find the appropriate value of D2. This is the table I was talking about. So here you can see, this is the sample size. For example, if sample size is 5, then constant D2 is here. There are many other constants that we use for other control charts. Then we can find the good estimator for standard deviation. Now let me go back. So this is standard deviation, estimator for standard deviation. And if you remember, what was the control chart equation? The control chart was CL is mu. So what is mu? X double bar. And UCL is mu plus 3 sigma. LCL is mu minus 3 sigma. So mu is X double bar minus 3. What is sigma? Actually, since we are using X bar chart, it should be divided by standard deviation by a squared root of n, because it's the variance of X bar. So it's 3 sigma square root of n, and this is sigma, which is R bar divided by D2 square root of n. The same thing here, X double bar plus 3 R bar divided by D2 square root of n, which we have exactly here. And we can do some simplification. Instead of using D2 constant, we can combine D2 and n, because both of them are constant, and define a new constant called A2. And this is the final equation that we use in practice. So this is the final equation we use in practice. What you do, you calculate X double bar, you calculate R bar, and then A2 is a constant from that table. And you can find your CL, LCL, and UCL. That's how it works. How about R chart? This is just the control limits for X bar. Okay, this is X bar chart. How about R chart? Here is the set of equations that you have for R chart. You calculate your R bar, then your center line is R bar, UCL is R bar times a constant, and LCL is R bar times a constant, which is D3. Here is one example. In this example, we want to monitor the inside diameter of bearings, produced bearings. For that, we collect 24 samples, and each sample includes 5 bearings. So the complete table should look something like this. So I have X1, X2 up to X5, and then you have these numbers here, and this is the average, and this is the range, which is maximum minus minimum. Then you have 24 samples. So M is 24. And what you do, you calculate the average, which is X double bar in this case, and you calculate R, which is R bar. We want to set up basically a trial control limit first. So n is equal to 5. Again, this is very important to know that this is based on n. The table and constant is based on n, not based on m. Now, n is 5. Therefore, the A2 constant that I use is here. This is D2, and this is capital D3 and D4 that I use for R chart. Now I need to calculate the control limits. So LCL and UCL, let me start with the LCL and UCL of X bar chart. So for X bar chart, I have UCL X double bar plus minus A2 R bar. So in this case, it would be 34. And I guess R bar was 4.7. So plus minus A2, which is point here, 0.577 times 4.7, which is R bar. That's the R bar that we have here. So based on that, you can get UCL and LCL here, and CL, which is the center line, is X double bar. How about for R? For R, you get UCL as D4 times R bar. Your CL is R bar, and your LCL is D3 times R bar. This guy is 0, because D3 is 0, and R bar is 4.7. And for UCL, I go back, this is D4, which is 2.115 times R bar 4.7. It gives you your UCL. So I get 9.96, 4.7, and 0 here. Now, as you can see, what happens, 2 points are out of control. We need to identify the root cause, take corrective actions, and the next step would be to remove these 2 points from calculations. So after removing these 2 points from calculations, we will have nu X double bar. Here, we need to add them up, add all these numbers up, except for these 2, divided by 22, because we lost 2 samples. And also, we calculate R bar, and based on that, we calculate all the control limits. So here is the revised limit, as you can see, and now everything is in control, so we do not need to do anything else. These are finalized control limit and baseline for phase 2 monitoring. One question is, in practice, when we remove points or samples, first of all, if the point is out of the X bar chart, shall I remove the point from R chart? Yes. And the reason behind that is the process is out of control. So there is something wrong with the process. So any points, it doesn't matter if it's mean or variance, is coming from an out of control should be removed. That's one point. The second one is, when you remove a point or sample, shall we replace it with a new sample? And the answer is, it depends. If there is a lot of samples being removed, then yes, you need to do that. Otherwise, if you are just removing 2 or 3 samples, that's fine. But if, let's say, you start with 30, but you end up with 10 or 15 samples, then you need to replace the samples with new ones. After getting the new sample, you calculate the new control limit and do the calculation based on that new sample. So a summary is that basically a slot summarizes what I said. In phase 1, what we can do and how we can construct X-bar and R control chart. By that, I finished this lecture. I'll see you in the next lecture, and where we learn how to use X-bar as control chart for monitoring. Thank you.